In our last lecture, we were talking about complex power. As a very quick review, the relationships that we developed were as follows. So the complex power S, which is measured in volt amperes, was equal to V effective multiplied by I effective cosine of theta V minus theta I plus J V effective I effective sine theta V minus theta I. And I simplified this to the relationship P plus JQ, where P was the average power measured in watts, and Q was the reactive power measured in volt amperes reactive, or VARs. And then we also had a polar form representation of our complex power. This was V effective, I effective with an angle of theta V minus theta I. And I said that this in a reduced form was our apparent power measured in volt amperes with an angle of our power factor angle theta S. So the first thing that I want to introduce that's new to you guys today is what's called the power triangle. Okay. So the power triangle is nothing more than a graphical representation of these relationships. And I find it to be a very handy way to remember which parts of complex power are doing which things. Okay. So let's put down here power triangle. Okay. And I'm going to say specifically here, for an inductive load, excuse me, and I'm going to note that the resistance of an inductive load will be positive, and the reactance of an inductive load will also be positive. Who remembers what resistance and reactance, what do those things mean? So those are the rectangular form parts of our impedance, right? So impedance in a rectangular form is R plus JX. So the real part of our impedance is resistance, the imaginary part of our impedance, so that's dealing with inductors and capacitors, is the reactance X. So when we have an inductive load, essentially it means that there's going to be some amount of resistance, and then the total contribution of the reactance, so all of the capacitances and inductances lumped together, will overall look more inductive than capacitive. So for an inductive load, the power triangle will look like this. So I'm going to put the imaginary axis as my y-axis, and the real axis as my x-axis. And what we should see is that our complex power vector will essentially be in the first quadrant of our complex plane, okay? So this purple arrow here represents our complex power. Okay? The projection of the complex power onto the real axis is our average power. Okay? And similarly, the projection of that complex power vector S onto the imaginary axis will be our reactive power Q. The length of this vector is going to be our apparent power. And the angle measured from the positive real axis up to our vector is our power factor angle. So from this simple triangle, we can see, that our complex power S for an inductive load will be P plus JQ in rectangular form, and the magnitude of S, angle theta S in polar form. Okay. So if we can draw our power triangle for any given load, and we can look at it and we can see some things that are going on, okay? Now, we're going to wind up using these power triangles here in a couple of minutes when we talk about power factor. But before I get into power factor, I want to give you guys an idea of what the power triangle for a capacitive load might look like. Okay. So a capacitive load is a load that will have some positive amount of resistance, but it will have a negative reactance. So I'm saying that our reactance X is less than 0 in this case. Okay. So for these capacitive loads, our power triangle will look like this, where now I'm effectively looking at what's going on in the negative imaginary direction and the positive real direction. So our complex power will lie somewhere down here in the fourth quadrant. Once again, actually, let me label that. So there's our complex power vector S. The projection onto the real axis will once again be our average power. The projection onto the imaginary axis will be our reactive power. And in these cases, when we have a capacitive load, our reactive power will always be negative. Okay. The magnitude of this vector is once again just our apparent power. And goodness, that looks horrifying. There you go. And the angle formed between the real positive real axis and our complex power vector will be our power factor angle theta S. So we're going to still get that same result of complex power S is equal to P plus JQ. In this case, Q just happens to be a negative quantity. And then we're still going to have the polar form relationship that we have our apparent power with the angle of our power factor angle. Okay. So if you're ever given a power triangle for a particular load, if it's in the first quadrant, you can know intuitively that we are dealing with an inductive load. If it's in the fourth quadrant, you'll know that we're dealing with a capacitive load. So I have a little bit of a conceptual question I would like to ask you guys. Why don't you think we're going to see any power triangles in the second quadrant or the third quadrant? Anybody have any idea? Yes, sir. So what part of it can't be negative? The resistance, exactly right. So there is such a thing as negative resistance, but it is pretty darn rare. And devices that utilize negative resistance don't utilize negative resistance over their entire operational range. It's just for brief portions. The most common example of negative resistance is actually the ballast in a fluorescent light system. Okay, so those have specific ranges where they will exhibit some negative resistance, but it's not something that most of us are going to deal with on a day-to-day basis. So for the most part, we just ignore the cases where negative resistances occur, which is exactly what would happen in quadrants 2 and quadrants 3, where we'd be looking at negative real impedances or negative resistances. So good job. All right, so I want to look at the in-class assignment, and we're going to work on parts A and B of this first problem before I introduce the concept of power factor to you all. Okay. So we can just call this the solutions guide for lack of a better word. So in this first problem, we are simply asked to determine our complex power specifically in polar form for various loads given the conditions in parts A through D of this problem. Okay. So in part A, we are told that our load is drawing a current of I as an RMS phasor is 9 plus J5 amps RMS. And we are also told that our voltage as an RMS phasor is 120 angle 32 degrees volts RMS. So my first question to you all is, how can we use these two pieces of information to determine the complex power for the load that has this current flowing through it and this voltage across it? So we are not looking for P, we are looking for S. And also P doesn't equal to IV in complex power. Okay. So we are doing complex power calculations. So you should be looking at your complex power notes. If I know the current and I know the voltage, what mathematical operation do I carry out in order to compute my complex power? This is a fundamental definition. No. Right? We have B and we have I, right? So why would we need to make anything more complicated than that? So whenever we have both the voltage and the current, we will simply use the relationship that our complex power S is the product of the RMS phasor voltage multiplied by the complex conjugate of the RMS phasor current. That is our fundamental definition for complex power. I believe I mentioned to you guys multiple times in our last class meeting that if we can perform this simple operation, we'll be good to go in the overwhelming majority of our cases. Okay. So my V is 120 angle 32 degrees volts RMS. What is the complex conjugate of my current going to be? We talked about what complex conjugate operation means in our last class meeting. What was that? 9 minus J5, exactly right. So the complex conjugate operation changes the sign on the imaginary part when we have a rectangular form complex number. So if I is 9 plus J5, then I conjugate will simply be 9 minus J5. So great job, thank you. So I would like for us to put this in our calculators. And I would like for one of you guys to tell me what the correct answer is. And I want to remind you specifically that I am looking for the result in polar form. If anybody needs any assistance on how to use their calculator, I would be more than happy to help. 1,235.5 with an angle of 2.9 degrees. Okay. That seems reasonable to me. It's pretty close to the answer that I provided to you all. Thomas. Sure. So I think my license for my virtual calculator has expired, but I can come over here and just show you how to do it pretty easily. Use the calculator a lot. The system's learning how to do it, pop over here. So for you guys with the TI 36X Pros, which is the suggested calculator for this class, all of your complex operations are buried in the pi key, right? So if you press the pi key 3 times, that's how you get your imaginary operator I. And if you press second in pi, that brings you to the complex menu where you get your angle operator. So for this, I would do 120, second complex 1 to give me my angle operator, 32. And then 9 minus 5, pi, pi, pi to give me my I. Close my parentheses. This gave me the result in rectangular form. So I can either press second complex and then 4 to give it my result in polar form, or I can change the mode and have polar form be the default, which is what I would actually prefer. Okay. We'll use polar form complex numbers as our answer way more often than we do rectangular.
Yeah. So that you had some that you don't need to do this?
Yeah. So that you're not allowed to do that calculator all day, stuff like that, right? I have no idea how to use it. So I press the math button, and then if you add over, that's where all of your complex the calculator will angle, the rectangular form and the solar form, but I know that six. All right. So for those of you that have figured out how to work your calculators, I believe we all got this result. So let's move on to part B. And after we wrap up the lecture and stuff, I can help assist you guys with your calculators further if necessary. All right. So in part B, we are told that our load draws 1,000 watts and 100 VARs at a leading power factor. So I'm going to have to give you guys a little bit of a hint here because we haven't talked about power factor yet. Whenever we have a load that's operating at a leading power factor, that will always be a capacitive load. So when I talk about that 1000 watts there, what part of the complex power am I referring to? What was that? What did you guess?
The real part.
The real part, okay. So you're 100% correct that it is the real part, but the real part of the complex power has a special name. What is it? Look at your power triangle or look at your notes.
Yeah.
The average power, absolutely right. So we are told that our average power is 1000 watts. And then we have a reactive power of 100 VAR. And I know that it's the reactive power because the units are volt amperes reactive. What's the symbol for reactive power again? Q, okay. So we're going to have Q is equal to 100 VAR. But I just told you a moment ago that this is a capacitive load, essentially. So should Q be positive or negative? Negative. So we're going to put a negative sign out front here. So essentially, my complex power is just going to be P plus JQ, or 1000 minus J100 volt amperes. Because I was given the real part and I was given the imaginary part, I can just put it in rectangular form. And then now I would have my calculator convert that from rectangular form into polar form. And so I'd like for you guys to take a moment and do just that, please. So 1004.987, so let's call that 988, with an angle of, what was that?
-5.7.
-5.710 degrees volt ampere. Great job. I need to get this calculator out of radian mode or it's going to drive me nuts. There we go. Okay. Yes. Three. Yeah. All right, so we can't really do part C or part D as of yet without a good understanding of what power factor is, how to calculate it, its relationships, and all that kind of jazz. So let's pop back over to our notes and let's talk about power factor. Okay. So power factor can be thought of as a means or a measure of the specifically electrical efficiency of a system. And I want to be clear about what I mean by that, because you guys have probably been familiarized with the concept of efficiency in your other classes, where that might be the ratio of the output divided by the input, okay? And power factor is similar to that, okay? So mathematically, we're going to define our power factor, PF. It will be equal to the ratio of our average power divided by our apparent power. And I'm going to put another relationship here to the right of this in a moment, but I want to talk about what this relationship means, okay? So I believe that I mentioned in class on last Thursday that the average power is what we as a consumer pay for on our electric utility bill, right? So average power is representative of what we consume. And the apparent power absolute value of S is essentially a measure of what the electrical utility supplies. Okay. So essentially, power factor is kind of what an electrical utility uses to, it's a figure of merit that an electrical utility uses to make sure that you're using the electricity that they produce, for lack of a better word, responsibly, right? Meaning that if you're only consuming a very small amount of average power, but they're sending you a whole heck of a lot of apparent power, then there's got to be something that's going on to where you're not consuming all of that power. So essentially what we've got, and I think we talked about this in our last class as well, right? Our average power is the part of the complex power that's capable of performing work. And then our complex power is the part of the complex power that represents temporary energy storage, either in capacitors or inductors. Well, if we were to look at the instantaneous power absorbed by a capacitor or an inductor, exactly half of the time they are absorbing power and exactly half of the time they are supplying power. So in a complex power perspective, that means that exactly half of the time that imaginary power or that reactive power is being sent out to the customer, and exactly half of the time that reactive power is being sent back from the customer to the utility. So that's not really a good thing from a money-making perspective, because they are having to pay money to generate that power. And that money that they are paying is in the form of either fuel for coal fire or natural gas plants. They're having to pay for it in the form of the infrastructure. So the size of the cables and things like that will effectively need to be larger. The more current and therefore the more electricity you send down the line and things like that. So the electrical utility effectively wants this ratio of P average to apparent power to be as close to 1 as possible for the overwhelming majority of the time, so that they are not spending a bunch of extra money generating electricity that literally just gets sent right back to them every half cycle of our sinusoidal system. Okay. So if we look at our mathematical definitions for average power and apparent power from class on Thursday, or actually we can look at just what we have up here, right? So if this guy right here is my average power, and this guy right here is my apparent power, what's left over when I divide average power by apparent power? Just that cosine term, right? So my power factor can also be expressed as the cosine of theta s, my power factor angle, which is literally why theta s is called the power factor angle. It's what's used to compute the power factor usually. So the reason why I prefer to use theta s to calculate power factor is because the sine of that angle will actually tell me a lot about what's going on with the load, okay? So I want us to effectively kind of develop a little table here that we can predict what's happening based on what the value of theta s is. So let's start with theta s is exactly equal to negative 90 degrees. Okay. So if we look at our power triangle for a capacitive load, Imagine that that angle theta s has swung all the way down to be negative 90 degrees. So in that particular case, what would our average power be? 0. Okay. So if our average power is 0, what is our power factor? What does it have to be? Also 0. Okay. So whenever we are dealing with a power factor angle of theta s is equal to negative 90 degrees, this means that our power factor is equal to 0 and our load is purely capacitive, meaning that we have no resistance and only negative reactance. So this is one of the two worst case scenarios from a power factor perspective, because we are operating effectively at 0% efficiency. None of the energy that is being produced by the electrical utility is actually being used to perform any work whatsoever. So not a particularly good case. Okay. Now let's say that our angle theta s is between 90 degrees and 0 degrees, but it is not including negative 90, nor is it including 0 specifically. Okay. So that range of angles is what we're looking at in this power triangle for a capacitive load. Okay. So theta s could be anywhere from slightly over 0 degrees all the way to slightly less than 0 degrees, all the way to slightly more positive than negative 90 degrees in this case. So we would always be dealing with a power factor angle that's in the fourth quadrant here. So this means that we are going to have a capacitive load. Where our resistance is positive and our reactance is negative. And what value do you guys think our power factor will have? Well, we know that at the very extreme of negative 90 degrees, our power factor was 0. So I think we could say that 0 will be less than our power factor. What's going to happen to our power factor when it gets the angle theta s gets close to 0 degrees? What's the cosine of 0 degrees? 1. Okay. So our power factor will range from 0 to 1 whenever our angle is between negative 90 degrees and 0 degrees. Now, whenever we have a capacitive load like this, and you guys potentially should have talked about this in your prior ENGT 221 class, but perhaps you didn't. So whenever we have a capacitive load, what we should observe is that our current waveform is leading our voltage waveform. So we're going to say that this is a leading power factor. So anytime we have a load that's operating at a leading power factor, we know that it is a capacitive load, okay? And all that leading power factor thing means is that the current is leading the voltage, or the current is hitting its peak value before the voltage hits its peak value, if we were to look at those waveforms on an oscilloscope or something like that. Okay. For what it's worth, if we have time at the end of the class, we literally might set up a simple little experiment here to show you guys what a leading and lagging power factor would look like on one of these scopes. But let's keep on going here. So now let's say that theta s is exactly equal to 0 degrees. So looking again at this capacitive load power triangle, imagine that theta s were 0, okay? So what would our reactive power be in this case? Are you raising your finger to say one, or you? So if we had, just as a quick aside here, so here's our real, here's our negative imaginary, and I'm saying that our angle is 0 degrees, which means our complex power would be literally on top of the horizontal axis. What's the value of the reactive power? 0. Okay. So that means that all of our complex power is real. Okay. So if all of our complex power is real, what's the ratio of P average to our apparent power? 1. Exactly right. They are the same thing. Okay. So we will have a power factor of 1. And this is commonly referred to as a unity power factor. Unity power factor is not leading, nor is it lagging. It literally just is a fancy way of saying the power factor is 1. Okay. So what type of load would a unity power factor what type of load generates the unity power factor? So let's look back at what happened when theta s was equal to negative 90. Okay. So when theta s was negative 90 degrees, we had a situation like this. Okay. So it was down here, right? We said that there was no real power or no average power, and we only had pure capacitance. Now we have the other side of that thing to where our load is purely real. So we essentially should have all of something and no capacitance. So what's that all of something? What is that something? Resistance, exactly right. So if all of our power is real, then our load has to be purely resistive. So R will be positive, and our reactance will be exactly equal to 0. So any resistor will always operate at a unity power factor. Okay. Now, if our power factor angle, theta s, is between 0 and positive 90 degrees, that's what's going on when we look at our inductive loads, right? So that theta s is definitely between 0 and 90. So this means that we are going to have an inductive load where R is greater than 0 and our reactance X is greater than 0. And our power factor is going to range from 1 is greater than our power factor down to 0, right? Because we know that when theta S is exactly equal to 0 degrees, our power factor is 1. And when theta S is equal to 90 degrees, well, the cosine of 90 is 0. Okay. These are what we're going to call lagging power factors. And they're called a lagging power factor because anytime our system has any inductance in it, our current is going to lag our voltage, meaning that the current will hit its peak value in time after our voltage hits its peak value in time. And then our last potential case is when theta S is exactly equal to positive 90 degrees. So in this case, our power factor will be equal to 0, and our load will be purely inductive, meaning that R is equal to 0 and our reactance is positive. So let's recap this very, very briefly, okay? So essentially, whenever theta S is equal to plus or minus 90 degrees, our load is just a pure energy storage element. Doesn't matter if it's a capacitor or an inductor. We're going to be operating at a power factor of 0. So completely inefficient. None of the power that's being sent to us as a consumer is actually being used to do any work whatsoever. As long as our power factor angle is between negative 90 degrees and positive 90 degrees, then some portion of the electricity that we are being sent will be used. The closer that angle is to 0, the more energy we are consuming and using to do useful things, okay? When theta S is negative, our system is going to be operating at a leading power factor. When theta S is positive, our system is going to be operating at a lagging power factor. And when theta S is 0, our system is operating at a power factor of 1 or unity power factor, meaning all of the electricity that's being sent out is being used to do something useful. Okay. So with those concepts in mind, let's look at parts C and D of this in-class example problem. So in part C, we are told that our load draws 450 volt amperes at a power factor of 0.65 lagging. So let me start by asking, what parts of the complex power does that 450 volt amperes represent? Is it average power? Is it reactive power? Or is it apparent power? Apparent power, okay? So we know that the magnitude of our complex power, which is the apparent power, is 450 volt amperes, because that's what the units of volt amperes tell us. Now we're also told that our power factor is 0.65 lagging. Our ultimate goal here is to get our complex power S, which will be in the form of our apparent power and then angle, our power factor angle, because that's what the polar form representation of our complex power literally is. So we already have our apparent power. The only thing we need to figure out is how to use power factor to calculate theta S. Does anybody have any thoughts? Arc cosine, absolutely right. Literally that simple, right? So this is going to be 450 with an angle of the arc cosine of our power factor, which is 0.65. Now, I want to make you guys aware of something, and this is actually pretty important. Your calculators, when you perform the arc cosine operation or the inverse cosine operation, it's always going to give you a positive angle as a result. So this is where that leading or lagging power factor comes into place. We learned just a moment ago that whenever our power factor angle is positive, that means we're operating at a lagging power factor. So our arc cosine always gives us a positive angle. So effectively, it's always going to work for lagging power factors. If we ever have a leading power factor, we need the angle to be negative. So we'll actually have to include a negative sign in our arc cosine operation to make the calculator spit out the correct result. Okay. So since we were told that this power factor is already lagging, I'm just going to put a plus sign here to remind me that my angle is supposed to be positive. And then I'm just going to throw this into my calculator, right? So I'll have 450 angle inverse cosine of 0.65. And I got 450 with an angle of 49.458 degrees. Volt amperes. Anybody else get that when they threw it into their calculators? See people shaking their heads. Yes, great job. So for part D, now we're told that our load is drawing 100 watts. So whenever I have the units of watts, what part of the power am I talking about? Average power, okay? So P average is 100 watts. My power factor is 0.75 leading. So once again, since I'm looking for complex power specifically in polar form, I'm trying to find my apparent power and my power factor angle. Well, we just figured out that if I know what my power factor is, I can do the arc cosine to get my power factor angle. So pretty obviously, over here, I'm going to wind up doing inverse cosine of my power factor. And because my power factor is leading, I need to put a negative sign in front of that inverse cosine operation to make sure my calculator gives me the right result. So now my question to you all is, how am I going to get my apparent power from average power and power factor? Exactly right. If we rearrange our ratio, power factor is equal to P average over apparent power. We could find that our apparent power is just P average over our power factor. Right? Just simple algebra. Excuse me, we would just switch the place of these two variables essentially. So our apparent power is just going to be P average divided by our power factor. So that's going to look like 100 over 0.75 with an angle of negative inverse cosine of 0.75. And I can put that whole thing in my calculator just like that. And I got 133.333 with an angle of negative 41.4096. So I'm going to call that 410 degrees volt amperes. See you guys shaking your head. I assume that means you got a similar result. Mark cosine, cosine. Okay. So this in-class assignment problem was really just to get us familiar with the different relationships, okay? We didn't have to do any circuit analysis or anything to do any of this stuff. They were all just given to us. So I'd like for us to start working on problem 2 now, okay? So in this particular problem, we have a 120 volt source, much like a volt RMS source, much like any outlet that we would see in our homes or anything like that. And it's connected to a few different impedances, okay? And then we're asked to determine some complex power related quantities, right? So average power, apparent power, reactive power. So instead of bothering to use all of those equations, V effective, I effective, cosine theta V minus theta I for average power and so on and so forth, what I want us to do is actually to calculate the complex power that is being absorbed by each of those impedances and the complex power that's being applied by our source, and then use the complex power to figure out the answers to parts A through D, okay? So, excuse me, having a mild asthma attack. All right, so let's start with our impedances because that's probably going to be the easier thing here, okay? So if we wanted to find the complex power absorbed by an impedance, what two pieces of information would we have to have? Voltage and current, exactly right. So I'm going to define the voltage drop across impedance A as this voltage VA with positive polarity terminal on the left. And I'm going to define this voltage. I'm going to call this VBC because it's the voltage drop over impedance ZB and impedance ZC since they're in parallel with positive polarity terminal on top. Okay. Now I'm going to define this current flowing into the positive polarity terminal of VA as my current IA. I'm going to define the current flowing into the positive polarity terminal of ZB as IB. And I'm going to define the current that's flowing into the positive polarity terminal of of ZC as IC. So if I can determine those 1, 2, 3, 4, 5 quantities, I can perform every complex power calculation that I need to, okay? So my question to you guys is, you have taken a class dealing with circuit analysis. Supposedly you have done that using some AC analysis, complex numbers and all of that kind of stuff. So how might you go about solving for literally any of those quantities. There are multiple different ways to do it, so I'm not looking for the best way or anything like that just yet. I just want to know how you guys think when you try to solve a problem like this. So top of your head, what comes to mind? How could you solve for literally any of these things? What would be your first step? Find the total impedance. Okay, so that is definitely one way to go about doing this. So let's run with that. Okay. So we're going to find the equivalent impedance here. ZEQ. Okay. So this is going to be the equivalent impedance seen by our voltage source. So describe to me, not looking for numbers or anything yet, what you think that equivalent impedance is going to look like. So ZB and ZC are in parallel, and that combination is in series with ZA. Perfectly correct. Okay. So ZA plus ZB in parallel with ZC. That shorthand notation there, I'm not sure if you're familiar with it, where I just put two vertical lines like that between two circuit elements. That means they're connected in parallel. That's a pretty commonly used shorthand notation. So if you haven't been introduced to it yet, you have now. Okay. So when you guys learn to do parallel combinations of elements, how did you learn how to do it?
But there's two you can multiply on top and divide by the added one.
Exactly. Okay, so I just wanted to make sure that you knew the shorthand way to do it, because that's the way that I'm going to do it for sure. But you are correct that that only works whenever there's two elements. So we could rewrite this essentially as ZA plus ZB times ZC over ZB plus ZC. Absolutely right. So I'm just going to take a moment here and put those numbers into my calculator. So ZA is 2 angle 15. And then I'm going to have ZB, that is 10 minus J5, multiplied by ZC, that is 8 plus J6. And then that'll be over 10 minus J5 plus 8 plus J6. And I'm going to get the equivalent impedance here. And I'm going to have it in polar form just because that's what I have my calculator set up for. So putting in 2 angle 15 plus 10 minus 5 I times 8 plus 6 I over 10 minus 5 I plus 8 plus 6 I. Excuse me. I got 8.187 with an angle of 9.0429. So let's call that 9.043 degrees. So before I move on from this, can anybody confirm that that's correct? It's always a possibility I put something in my calculator wrong. You're shaking your head that I got it right. Anybody else? All right, got 2 thumbs up, so I think we're good to go. So for what it's worth, this little A that I'm putting in quotation marks there, I like to store things in my calculator, especially when I'm dealing with complex numbers, just because there's so much bookkeeping involved. And if I don't do that, I'm going to wind up with lots and lots of rounding error. So I'll use stored values to figure stuff out. Okay, so we figured out what our equivalent impedance is. So how could we use that to find Anything else? Okay, so we could use Ohm's law to figure out what our current IA is, since that's the current that's flowing out of the positive polarity terminal of our source and just into the network as a whole, okay? So we could say that IA is just going to be Vs divided by ZEQ. That's just Ohm's law rearranged. Well, Vs, we were told that that's 120 angle 45 degrees. And then ZEQ, we just found to be 8.187 angle 9.043 degrees ohms. So I'm going to throw this into my calculator, 120 angle 45 divided by what I have stored as A. And I got 14.6565. So let's call that 14.657 with an angle of 35.957 degrees, amps RMS. And I'm storing this as B. Okay, so now that we know what that current is, how can we solve for any of the other quantities? So we can. How would you suggest that we do that? Okay, so I wasn't sure if you guys were aware of current division, but absolutely. How did you guys learn current division? Okay, so what you just suggested is we could say that IB is the current that we just found as IA times the ratio of ZC over ZB plus ZC. That's what you suggested, right? That is technically correct. That being said, I don't particularly like that representation of current division. So let me explain why, okay? So this mathematical equation, where you effectively take the current, in the numerator, you put the element you're not interested in, only works when you have exactly two parallel paths. But we can have more than two parallel paths. So what I'd like to do really quickly here as kind of a tangent is show you how current division can work for an infinite number of parallel paths so that you'll have more of a general purpose expression for current division, okay? So we'll do this over here in the notes section. This is an aside. So I'm going to call this just quickly current division revisited, okay? Now, I'm not going to bother with deriving this for you guys because I have that on my Engineering 221 YouTube videos and all of that kind of stuff. So I'm just going to hit you with the equation and show you that it is literally identical for exactly two things in parallel, okay? So if we have a network containing multiple resistive paths in parallel, and I'm going to define these just as generic impedances. So let's call this guy ZA. Here's ZB, all the way out to some impedance. Let's call this guy Z sub n, okay? Where this just represents the last one. And let's say that I have some known current that's flowing into this network, and I'm interested in finding the current flowing through one of these individual impedances, like so. The kth impedance, so what I mean by that subscript k there, that's just whichever impedance I'm interested in, okay? Or the current flowing through whatever impedance I'm interested in. So if I was interested in the impedance through ZB, I would replace K with B, okay? So anyway, so that's going to be our known current multiplied by a ratio. But instead of doing what you guys have seen before, I'm going to choose to write this ratio as 1 over Z sub K divided by 1 over ZA plus 1 over ZB all the way out to 1 over Z sub n, like so. So this looks a little bit more complicated, and honestly, it is. But the reason why I prefer this particular form for current division is because it's consistent, meaning that if we want to find the current through ZB, ZB goes in the numerator. It's not the other thing. Okay, so it looks a little bit more like the voltage division relationship. You guys learn about voltage division?
Yeah.
Yes, okay, good. So in voltage division, you just put the resistor or the impedance that you're interested in the numerator, and then the sum of the impedances in the denominator. Here we have the reciprocal of the impedance we're interested in the numerator, and the sum of the reciprocals of all of the parallel paths, okay? So just for what it's worth, when we have exactly 2, so let's say that I had a network like this where I had just Z1 and Z2, and I was interested in finding I1, and I know the amount of current flowing into the network, then that would be I1 would be equal to my known current times 1 over Z1 over 1 over Z1 plus 1 over Z2, okay? Now, right here, I'm just going to show you that it's equivalent to the way that you learned it, okay? So what I'm going to do is I'm going to multiply this 1 over Z1 by a factor of Z2 over Z2, because that's just a fancy representation of the number 1, right? And I can multiply 1 over Z2 by Z1 over Z1, like so. And what that's going to do is it's going to give me I known times 1 over Z1. And now I have 1 over Z2 over Z1 times Z2 plus Z1 over Z1 times Z2. So essentially, I've got a common denominator in my denominator. So that's going to look like Z1 plus Z2 over Z1 times Z2. How do I divide 2 fractions? Multiply by the reciprocal. Absolutely right. So instead of having 1 over Z1 divided by Z1 plus Z2 over Z1 times Z2, this is going to come out to be I known multiplied by 1 over Z1 multiplied by Z1 times Z2 over Z1 plus Z2. And then my Z1 cancels this Z1 here, and I'm just left with I known times Z2 over Z1 plus Z2. So it is exactly the same way that, or you get the exact same result as how you guys learned it. But the thing that I just showed you works for any number of parallel connections. Yes, sir.
So in the top equation right there, IK, for the numerator, 1/ZK.
Mhm.
What is ZK?
Whichever parallel path we're interested in. So if we were interested in ZA, or the current Z or IA, everywhere we saw K, we would just replace it with A. So over here, for what it's worth, so we could say that IB would be IA, that's our known current, right? We just solved for that. So IA is flowing into this node, and then it's dividing between impedance ZB and impedance ZC. If we want the current flowing through impedance ZB, then we would have 1 over ZB in our numerator, and then we would have 1 over ZB plus 1 over ZC in our denominator. So just to repeat, the I sub K or whatever is just the current through whatever impedance we are interested in. In this case, we are interested in the impedance, or excuse me, the current flowing through impedance ZB. So everywhere that we saw K, we replaced it with B. If we were interested in the current flowing through impedance ZC, everywhere we saw K, we would just replace it with C, and so on and so forth. Yes, sir.
Is that for the nominator, whatever you?
This one on the left is B. It just I didn't write it down or press hard enough on my stylus for it to show up the rest of the B, but it is 1 over ZB plus 1 over ZC. So we're at a point now, I'm just going to write the numbers out here. So this would look like 14.657 angle 35.957 degrees amps RMS. Then I would have 1 over ZB, which was 10 minus J5 ohms, divided by 1 over ZB, once again, 10 minus J5, plus 1 over ZC, where ZC is 8 plus J6. And I'm going to throw this into my calculator. And I got 8.12999, so let's call that 8.130 with an angle of 69.647 degrees amps RMS. And I'm going to store this in my calculator as C. So before I move on from here, can anybody confirm that that's correct? Okay, got several people shaking their heads. So If we wanted to find IC, we could do current division if we were so inclined. So I'd like for you guys to kind of practice and tell me what that current division relationship would look like here. Okay.
Divided by 1/ZB plus 1/ZC.
Exactly right. So 14.657 angle 35.957 degrees amps RMS. 1/8 plus J6 divided by 1/10 minus J5 plus 1/8 plus J6. Absolutely. I'm actually not going to bother typing that into my calculator. I'm going to use Kirchhoff's current law because I'm lazy. I just wanted you guys to have practice. We could also say that IC is just IA minus IB. So that's what I'm going to put into my calculator because I already have those things stored, but you'll get the same result either way. So alpha B minus C. So I got 9.0896. So let's call that 9.090 with an angle of 6.212 degrees amps RMS. And I'm going to store that guy as D. Anybody get that result? Good deal. Okay, so now that I know every current, how would I find those missing voltages? Ohm's law. Perfectly reasonable, okay? So VA would just be IA times ZA. So that would look like 14.657 angle 35.957 degrees amps RMS times ZA, which was 2 angle 15 degrees ohms. So let's see what I have stored in my calculator as B times 2 angle 15 gives me 29.313 with an angle of 50.957 degrees. Volts RMS, I'm going to store this as E. And VBC could be IB times ZB, or it could be IC times ZC. Either one of those will give us that voltage because they're in parallel. I'm going to choose to do IB times ZB. So that would look like 8.130 angle 69.647 degrees times 10 minus J5 ohms. Which I got to be 90.896 with an angle of 43.082 degrees. Volts RMS, which I'm storing as F. And just for the hell of it, I'm going to put in IC times ZC in my calculator and make sure I get the same result. So 9 point, actually, let me do this easy way. What I have stored is D times 8 plus J6. And I did indeed get the same result. For what it's worth, since you guys are aware of voltage division, I personally would have used voltage division to find VA and VBC without finding the equivalent impedance, and it would have just eliminated a step. And then I would have used voltage division to find those two voltages, and then Ohm's law to find all the currents. Slightly faster, but doesn't really matter. All right, so now that we know all of these voltages and currents, how could we find the complex power absorbed by impedance ZA? So VA times IA conjugate. Yes. Okay. So let me, let's see, edit page. I want to insert a page. Crap, hold on. I'm just trying to give myself another blank sheet of paper on here and I put it in the wrong place. There we go. Just so that there's plenty of room here. Okay. So the complex power absorbed by element A, or ZA, is just going to be VA times IA conjugate, right? Where VA was 29.313 with an angle of 50.957 degrees. Volts RMS. IA was 14.657 with an angle of 35.957 degrees amps RMS. So how do I make that IA conjugate? Negative angle, absolutely right. So I'm just going to put a negative angle right here. And I'm just going to throw this into my calculator. So for what it's worth, your calculator can do the complex conjugate operation for you. So since I stored all of these variables in my calculator, what I'm going to wind up doing is just E, which is what I stored VA as right here. And then I'm going to do the conjugate of B, which is where I stored IA. So times conjugate of B, and I got 429.629 with an angle of 15 degrees, volt amperes, in polar form. And I'm now going to convert this result into rectangular form. And when I did that, I got 414.9899. So let's call that 990 plus J 111.196 volt amperes. So before we move on from this, how many of you guys were able to replicate those results? See a couple of people raising their hands, so good deal. So if I look at problem 2, part A, it specifically asked me to determine the average power absorbed by that impedance. So which one of those 4 numbers corresponds to the average power? 414.990. Absolutely right. So this guy right here tells us that PA is 414.990 watts. So the real part of the rectangular form is our average power. Okay. Yes, sir.
And so for the calculation, we did the 2 stored values. You stored IA as like the regular number,
Mm-hmm.
and then do like the conjugate of that would actually be 1 over the negative square.
Oops.
I don't have anything to store about it.
Option 6 is the conjugate. So if you go clear this out, you go into your complex menu, you say second complex, and then you scroll down. Option 6 is how it does how the calculator do the conjugate for you.
Thank you.
Yep. Which is how I just did it, by the way. All right, so let's move on to finding the complex power for impedance ZB. So how are we going to do that? Exact same way we did it for ZA. Okay. So we could say that SB was equal to VBC times, excuse me, IB conjugate. Well, VBC we found to be 90.896 with an angle of 43.082 degrees. Volts RMS. IB was 8.130 with an angle of 69.647 degrees. Amps RMS, and we need to conjugate that, so that's where that negative sign in front of the angle is coming from. And I'm going to throw this into my calculator. So for what it's worth, I have VBC stored as F. So I'll do alpha F times the conjugate of alpha C. And I just got 738.985 with an angle of negative 26.565 degrees. And in rectangular form, that looks like 660.968 minus J 330.484 volt amperes. For part B of the problem, actually, let me just put a note here. A, B. So for part B of the problem, we were asked to determine the apparent power absorbed by the impedance ZB. So which of those 4 numbers is the apparent power? The 738.985. Absolutely right. So for part C, we're going to find the complex power absorbed by impedance ZC. We're going to do it the exact same way that we've been doing. So VBC times IC conjugate. So that'll be 90.896 with an angle of 43.082 degrees, volts RMS. And then our current in this case is going to be 9.090 with an angle of 6.212. And I'm going to make that angle negative because I need to do the conjugate. So in my calculator, this is going to be, I think, F times the conjugate of D. And I got that to be 826.210 with an angle of 36.870 degrees, volt amperes. And converting that over to rectangular form, I get 660.968 plus J 495.726 volt amperes. In part C, we were asked to determine the reactive power absorbed by the impedance ZC. So which of those four numbers is the reactive power? The 495.726. So QC is, excuse me, 495.726 var. All right. So for part D, we are asked to determine the power factor at which our source is supplying power. There are a multitude of different ways that we could actually do this, given all of the information that we have, okay? I think the most straightforward way would be to calculate just the complex power, okay? So we're going to do it that way, and then I'm going to show you a slightly different way to do it. Actually, I'll show you two different ways that we could do it. So let's start with simply calculating our complex power the quote unquote normal way, okay? So that would be the voltage drop across the source multiplied by the conjugate of the current. Well, our source voltage, so that's just going to be VS times IA conjugate, right? So that would be 120 angle, I think it was 45 degrees, volts RMS. Let me double check up here. It's been so long. Yep, 120 angle 45. And then IA was 14.657 change. Negative 39.957. So 120 angle 45 multiplied by conjugate of what I have stored in here as B, if I'm remembering correctly. Let me scroll up. Yep. I got 1758.787 with an angle of 9.04299. So let's call that 043 degrees. Volt amperes, or in rectangular form, 1736.926 plus J 276.438 PA. So from this complex power, how could I determine my power factor? Yes, that power factor angle of 9.043 is probably the easiest way to do it if we know the power factor angle. So what do I do to that angle? Cosine, yeah. So the power factor at which our voltage source is supplying power is just going to be the cosine of 9.043 degrees. So I want the cosine of argument of my previous answer. And I got 0.98757. So let's call that 0.988. Is this power factor leading or lagging? It is lagging. Why is it lagging? You're correct. Because the angle is positive. Absolutely. Yep. So that's one way for us to do this. Perfectly reasonable. There are a couple of different ways that we could do this as well. I just want to touch them very, very briefly. Okay. So we calculated our complex power supplied by our voltage source by doing Vs times IA conjugate. Another way that we could have calculated that quantity SVS. So let me just put alternative number one. The complex power supplied by our voltage source has to be equal to the complex power absorbed by all of those impedances, right? So instead of doing V times IA conjugate, we could have just done SA, plus SB plus SC. So I'd like for you guys to take a moment and just throw those three numbers into your calculator, add them together, and confirm that you do get the exact same result as we got above, right? So that would be 429.629 angle 15. Sorry, 629 angle 15. Then we would have 738.985 angle negative 26.565. Plus 826.210. Angle 36.870. So 429.629 angle 15, 738.985 angle negative 26.565, 826.210, angle 36.870. When I added all those together, I got 1758.786 with an angle of 9.043 degrees. So this angle right here is literally the exact same thing. So we would obviously get the same result. Okay. Alternative number 2, just for what it's worth. I believe I mentioned to you all in yesterday's class meeting that the angle, the power factor angle theta s is the same thing as the angle of the impedance. So if we go back up to having ZEQ was 8.187 angle 9.043 degrees. Taking the cosine of that equivalent impedance angle would also have gotten us the exact same power factor. Okay. So all of these things are related to each other. Okay, so we only have 5 minutes left of class and there's still another in-class assignment problem. So I want you guys to take your ICAs with you and bring them to class with you on Thursday. We'll finish up problem 3. Another thing that I want to show you just very briefly at the beginning of class on Thursday are some alternative relationships. So there's nothing wrong with what we did today, but we can do it slightly more efficiently. And so I want to show you guys how to do that. All right, so that's enough out of me for today. Thank you guys for your attention. I will see you on Thursday.